Hello, welcome back to the next seminar about this workshop funded by NSF. In this seminar, my colleague Carlos Trujillo is gonna help me to present you the new advances in the hardware for the optical holographic microscopes that you're gonna find nowadays. So the learning objective of this seminar is we're going to talk about the basic foundations of the optical recording stage in a digital holographic microscopy. We're going to able to show you where are the difference of telecentric versus non-telecentric imaging systems. When we say that a system, a DHM system is working in an image plane, we're going to talk about it and what are the advantages and disadvantages in every case. We're gonna talk about if the system works in line of slightly of axis configuration. That means that we need to do phase shifting holograms. So we're gonna talk about what are the mechanisms, how we can provide that phase shifting holograms to the required configuration for the software. We're gonna also recognize how systems are gonna work in reflection mode. So usually biological samples are reflected, but DHM is also used for material science where the samples are reflective. So we're gonna show how reflective DHM systems they work. And then we're gonna talk about common path DHM systems versus the dual path interferometer setups and the advantages of them. So the question is, why DHM system is so useful in biology and material science. So let's talk about first in biology. Some applications about DHM system is for live cell imaging. The technique only requires a single shot, only a single image. So that's super useful because it's really fast, allowing to track the particle dynamics. It's completely quantitative, so we can analyze cells and tissues. Because the quantification, we can diagnose some diseases, we can screen diseases, we can understand what is the pathology of the cancer cells, and all those features can also be used for drug discovery. So if you're a live biological system, you apply a drug, and then you can analyze what is happening to the cell. It's like, for example, is the motility changing, or are you distorting something, or the cells are gonna get dead after a certain time. So all those different applications can be used using DHM systems. In terms of material science, DHM systems are also widely used to image the surface and the topography of material samples. For example, we can analyze the surface topography, we can see if there are some defects, we can determine what is the roughness of a surface, so that's going to be for quality control system. We can characterize the type of surface, that's really important for forensic examination. As you see here on the video, this is completely dynamic, so we can see how the topography changes in real time, and also for analyze MEMS electronic devices.
So, considering that DHM is an hybrid imaging method, that is, we need two stages to properly recover information from the sample. In the first stage, we need an optical setup, and in the second stage, we process the data. In this talk, we're going to discuss the optical setups. So, what's the DHM optical setup? In this case, is the one that is displayed on the right side of the slide, and you can see that we have a Mach-Zender-like interferometer. One of the arms of the interferometer is a microscope, a bright field microscope essentially, and this one magnifies the information of the sample that is scattered and therefore encode in the object that illuminates the sample, and it is quite at the sensor camera, a place where this object waveform, we can call it, is somehow superimposed with the reference waveform, which is a plane waveform. In this case, what it is recorded in the sensor camera is what we call the digital hologram. So mathematically, the hologram is composed by four terms. The first two terms in this expression do not carry any information about the phase of the object and the angle of the reference wave. So it is like it is called the dc term, and we need to somehow remove it from the recovery or retrieval procedure. The third and fourth terms, that is this one over here, name the object and the virtual image, or the twin images, the +1 diffraction order information or the -1 diffraction order information if you like, encode the whole sample information, both in amplitude and in phase. So the idea is to retrieve the information from the hologram of one of these two terms. Okay, if the hologram is acquired in an image plane configuration, that is, we have conjugated planes between the camera sensor plane and the sample sensor plane, well, in that case, the only procedure to recover the information of one of these two terms is a spatial filtering procedure. But if we have an out-of-focus acquisition, then we need to propagate the complex amplitude that is recovered in this step. Okay, so in the optical recording of DHM holograms, we have essentially two different kind of setups, both the off-axis setups and the inline setups, also known as on-axis setups. So recording the hologram spectrum, we notice that the information of the DC term and the +1 and -1 diffraction order can be are the ones that build the whole hologram, and according to or depending on the position, the location of this information in the hologram spectrum, we can have the information of the different terms completely isolated, like in the case of an off-axis recording or off-axis hologram, or completely overlap. In this case, we have the information of the diffraction terms and the DC term, or in the same exact position or center at the same point. We have an intermediate situation, which is the one in which the reference angle, which is used, or the angle of between the interference wave, is slightly off-axis. That is not exactly completely diffraction limited off-axis acquisition. It is a situation in which the information of the +1 or the -1 diffraction order is somehow overlapped within the DC term, but is not completely centered. And yeah, in a previous talk, we said that when we have inline setups, well, the straightforward way to recover information is by using phase shifting methods in DHM, also known as phase shifting DHM. But to do this, in terms of the optical setups, we have different setups, in fact. I would say the most conventional one is the one that uses a piezoelectric locator or translation stage, in which the location of the mirror, in this case the mirror of the reference waveform, is somehow controlled, so we can change the optical prime length of this waveform with respect to the optical path weight of the object weight that is somehow kept constant. So at the end, what we will have at the recording camera sensor is a hologram that is phase shifting according to the location of this mirror. We also have situation in which we can use polarization, that is, we can, for instance, have circular polarized light, and we can make an impinge on a rotating half-wave plate, and we can obtain then different phase shifted holograms too. We can also use diffraction gratings to obtain different version of the hologram with different phase shift, and we can also, of course, use a wave plate, essentially a plate of glass, in order to produce, depending on the angle of the rotation of this plate, we can have different phase shifting holograms as well. Okay, all the latter configurations require somehow mechanical control of the phase shift, but we can also have these phase shifting DHM setups using, for instance, spatial light modulators, and that can be controlled in a computer. This is somehow a very easy way to control the phase shift, but at the same time, well, you need a driver and a control in a computer of the setup, so it can be a little bit more expensive. But you can also have different methods, different optoelectronic mechanisms to obtain this kind of phase shifting holograms. For instance, you can use electronically tunable lenses like this one over here. So you can control the exact value of the focus of the electronic of the ETL lens, and that way you can control the change in the optical pan wave of the reference wave. And as previously done by the mechanical methods, you can control in this way the phase shift that is finally produced in each one of the DHM holograms. Other methods to produce phase shifting or to recover or to record DHM holograms is by using simultaneous or synchronous acquisitions of DHM holograms. For instance, in this very complex and very difficult to align configuration, we have 4 outputs in these 2 coupled Mach-Zender interferometers, and we can see the idea in this case is that we can control by accurately positioning one of the mirrors, we can obtain a phase shift of the holograms that are acquired in cams 3 and camera 4 with respect to what is obtained in camera 1 and camera 2. But at the same time, we already know that the two outputs of one single Mach-Zender interferometer, for instance, this one over here, well, we can obtain, we have in fact a P shift between the two DHM holograms. So we have a P shift between this one, and we also have a P shift between Cam 2 and Cam 3 recordings. Well, we only need to guarantee a P divided 2 shift between this interferometer and this one over here, as I mentioned, with the accurate control of the mirror M3 in this setup, for instance.
So in the previous slide, my colleague, Dr. Trujillo, showed a way where we can record phase-shifted holograms using several cameras and dual path interferometers. But there are also some approaches to do that in a common path system using a single camera. So the way of doing that is kind of multiplexing your camera. So having within the same field of view of your camera, putting together the three phase shifted holograms. And one way of doing that is using a diffraction grating. So like what we have here. So we have a diffraction grating that displays on the image plane. Well, it's placed in the Fourier domain, and in that way we have here a relay system. So we place the image plane of the objective lens is now placed, is moved to the sensor camera. So we have 3 different replicas, 3 different orders, 3 different beams coming for the diffraction grating, and each of them have a different phase shift, as we can see here from the images. So using this phase shifted hologram, we make the corresponding subtraction of the images to at the end reconstruct the phase imaging. And this is for the particular silica microspheres where the thickness was around 4 microns, and because it's quantitative, we can realize that that's really the thickness that we are getting. So let me talk about what is the meaning of telecentric versus non-telecentric imaging system, right? So first of all, the sensors can be placed at the image plane of the imaging system or in a different image plane, so the images are going to be recorded, therefore focused, and that's why we have here this convolution with the free propagation, the free space propagator, right? But let's assume that we ignore right now this stage because the free space propagator is convolved with the complex amplitude distribution of the object placed at the image plane of the microscope. And if we go into details here, what we have is a quadratic phase factor multiplying the 2D convolution of a scale copy of the complex distribution of your sample with the Fourier transform of the pupil of your microscope objective lens. And when this quadratic phase factor it depends on the optical configuration of your system, be completely optically removed. So this whole quadratic phase factor, the value is 1 if the system works in telecentric regime. So what that means is that the pupil plane of the microscope objective lens coincides with the front focal plane of the tube lens. So you illuminate your object with a plane wave, and after the tube lens you have another plane wave. So another way of saying is that the microscope objective lens and the tube lens are arranged in a focal configuration. So for this particular case, the complex amplitude distribution at the image plane does not distort by any additional quadratic phase factor. So that is the particular case where we're going to say that the system is shape invariant. So that means that a particular object is going to get placed by any place within the field of view, and we're always going to have the same response, and it's because there is no additional spherical phase factor distorting it. So here it's like an example, right? So we have this kind of object right there. So if the system is working in a non-telecentric regime and you cannot get the distribution of your sample, you're gonna have that your sample information is gonna be distorted by a quadratic phase factor. And you can say, fine, I have a quadratic phase factor here, but let's try to remove it. So let's say that you want to have a single shot technique, right? So you want to remove it, so you just need to compensate for that quadratic phase factor. One way to compensate it is to estimate the center. So you know, like the center of the quadratic phase factor is here, and then making profiles and fitting, you can know the curvature along the x and y axis, and you create kind of like the synthetic or the digital conjugated spherical phase factor to compensate. So this is kind of like the compensated image of your sample, and on the bottom, on the below row, what you have here is the sample image that you're gonna have using a telecentric imaging system. So you're gonna see that the raw phase image reconstructed is not distorted, and this is the corresponding 3D topographical image. So both of them look quite similar, like quantitative, it's kind of roughly the same. But if you kind of look kind of like the edges, you're gonna have like a kind of like a shell structure. So that means that it's close enough, but kind of like the background should be completely flat, right? And that's what you are seeing in the image. The background of the sample is kind of flat within the experimental errors. But when the system operates in non-telecentric regime, there is always kind of like a residual phase factor, which makes that your system is not anymore accurate. And that means that if your object is here, you're gonna have different values. So if your object is, for example, here, because the reconstruction is not perfect. And this is our like some particular case where I'm showing how important is the location of the field of view based on the compensation of the spherical phase factor. So what we did here is we simulate two spherical kind of discs, two discs placed in the middle and in one edge of the image field of view. And if it's telecentric, obviously the two discs are completely equal. So here, if you see kind of like the red profile, we're gonna have exactly the same value. However, now for the non-telecentric, I assume that we are like 5 pixels off from the center, and then around 5%, less than 10% off of the curvature of the real microscope. And this is our error that definitely in an experimental environment are easy to get achieved since you don't have any prior knowledge about the quadratic phase factor at the center. And when the disc is placed in the middle of the field of view, you can see that there is no difference or significant difference of the quantitative phase values, especially if this is experimentally within the experimental error we don't gonna have any difference here. But as far as we put the disc in one of the edges of the field of view, you're gonna see how different is the retrieve, the reconstructed phase. So these values, you're gonna assume that your sample is distorted. So let me give you a particular example. So using DHM, there has been used DHM to discriminate healthy versus malaria infected red blood cells, right? So let's say that you are assuming that some kind of distorted shape, you have a red blood cell that is malaria infected. And if it's completely uniform, your cell is healthy. But in this particular case, you are getting some distorted red blood cell. And it's not because it's malaria infected, it's just because your system is not well compensated. So there is still some residual spherical phase factor, which might give you some misleading analysis later if you want to quantify or analyze cells. So for that particular case, this is the main advantage of telecentric based imaging systems. And a part of accuracy for the first from the raw phase reconstructed image, the complexity of the reconstruction algorithm is less. So they are simple and they are faster to be implemented. Another advantage about using telecentric based DHM systems, regardless with non-telecentric, is that the resolution. So when you have telecentric based system, you have here the 3 replicas of the hologram, right? And you can see that within the 3 replicas, the object spectrum is placed at the interference angle, but it's symmetrically around a circle. And that circle is related with the pupil size of your objective lens. But when the system is arranged in a non-telecentric regime, now the defocus, or kind of like a distorted version of your object spectrum, now is not enclosed anymore in a circle. It's like it's the convolution of your object spectrum with a quadratic phase factor, giving you change the shape of the plus and minus 1 order and being kind of enclosed within a rectangle. So the bigger is the quadratic phase factor, the bigger is going to be the size of the rectangle. And if you want to have really good reconstructed phase image without any distortion, means that you need to avoid any overlay with the DC term. So if you have your quadratic phase factor bigger, effectively to don't have distortions coming from the DC term, you need to reduce the pupil of your microscope objective lens, which is gonna result in a reduction of the resolution capability of your system. And that's what we can see here from the top row. So this is a use of target, and as you're gonna know, the use of target cannot be able to discriminate what is the minimum resolvable element of the user target. It's a way to know the resolution of your system. So for example, here the minimum one is like the 5-6 element. So now if I go to the second column, I think it's the 5-3. This is the last element that I can see with my eye. But in the moment that we further reduce the pupil, the effective pupil of the microscope is probably the 5. I don't know if the 2 or the 1. But we keep reducing the resolution. So the system is not anymore limited by diffraction. So, and that's not what we want. We want to have the highest resolution as possible. So that's another disadvantage of using non-telecentric imaging systems. In other words, you want to preserve the resolution, you want to have a DHM system with the highest accuracy across the field of view and with minimum computational methods. Your system to be implemented is a telecentric DHM system.
Okay, but we also can have a telecentric DHM system working in reflection mode. That is essentially for non-biological samples. Well, in this case, we can the straightforward way would be the use of Mach-Zender-based interferometer. That would be the simple situation. But in here, I'm showing you a proposal that involves a system that can be both used for transmission and reflection samples. In particular, in this version that you can see on the left, you will see that this one is a pure reflection-based setup. We have a tight telecentric configuration established between the tube length and the microscope objective, of course. The information of the camera planes is recorded in image plane, and this method, as I previously mentioned, is particularly useful for non-biological samples, essentially reflecting samples made of some metallic surface or some metallic components. So, for instance, with the MEMS or with a reflection USAF test, we can see that the sensibility of the method is considerably increased in this setup, and at the same time, we can keep the resolution within the limits provided by telecentric limit.
So let's talk about right now about common path versus dual path interferometer. So far all the systems that we have talked are dual path, right? Which is the simple Mach-Zender or a Michelson interferometer, but the beam coming from the laser is split from the beginning. One of the beams is used to illuminate an object and the other one is to create a uniform reference wave. But those dual path interferometer are really sensitive in terms of the temporal fluctuation. So each of the beams travel different optical paths, so they make them less sensitive or less robust to fluctuations. So sometimes the interference fringes might fluctuate or you might not even see them. The other problem about is that the amount of optical elements that you're gonna have, right? So you're gonna have more optical elements, so you're gonna increase the cost of the system. So for that applications, it's kind of like the advantages of common path. So common path is just the goal is to have an optical element to kind of create the self-interferences of two replicas of the object. And the difference is that the two replicas of the object are gonna be slightly displaced laterally, and they are highly portable. They are compact because the only difference is just using one optical element. They have been used to be adaptable in a commercial microscope, so that means that you can further reduce the price because you don't need to duplicate already a microscope. You can just have a commercial microscope and add some kind of like external module to create your DHM system. People has created those kind of like common path DHM system using 3D printer parts, so definitely reducing a lot the price of the system. And the whole thing, those whole advantages without the resolution or the single shot or any of the feature of DHM technology. Here what we're gonna talk is about a different way of doing common path DHM system, and it's using a Fresnel by prism. So let's assume that we introduce a Fresnel by prism after the tube lines. So if the system works in telecentric regime, now the Fresnel by prism is going to create two replicas of the beam, and if the sample is illuminated with a plane wave, here we're going to have two plane waves where they are slightly displaced, so they are tilted. So two of the beams, they come from the same coherent beam, so they are coherent with each other. So at any plane after the Fresnel by prism, we're gonna have some interference fringes. So here is how we have the interference fringes here at the edges. Because the Fresnel there are some diffraction effects coming from the edge of the biprism, but the Fresnel biprism is illuminating with a plane wave. So regardless the position of the Fresnel biprism, we have fringes that they have the same lateral period around, and the lateral period depends is related with the refringence angle of the Fresnel by prism. So as I was saying, if you cannot place the Fresnel by prism in a different position, the lateral period of the fringe does not change. So that means it's invariant of the actual position of the Fresnel by prism. We're gonna change the field of view, but not the lateral frequency. And then we have verified experimentally that the experimental and theoretical fringes agree. So let's talk about performance, right? So we want DHM systems that they are limited by diffraction. So we image the use of target, and that's a high resolution phase use of target, and we make a profile. So we converted the phase into thickness because we knew the refractive index of the material of the phase target, and then we make a profile along the horizontal elements of the group 9, and this is the profile of the optical thickness. And we cannot estimate what is the minimum resolvable element that we can see in the 3 horizontal lines, and that's definitely the element 93. And if you go to the specification, that means that the separation with the horizontal lines is 775 nanometers, which kind of agree with the theoretical limit imposed by ABET. And we know that ABET is fully a restricted element, that you don't need to go through the ABET. The other one that we use from the same phase target is a star target. So we image a star target, and through this radial profile we get the profile, because we want to have a system that is accurate regardless the position of the sample, right? So this target is radially symmetric, and as you can see, the phase within the experimental errors, it's invariant of the position. Definitely both the use of target and the star target, the reconstructed techniques agree with the one mentioned by the manufacturer, which was 150 nanometers. So it's super great to have common path imaging systems, but as I was saying, they are based on the self-interference of two laterally displaced replicas of the object, right? So this is one replica of the object, and I have another replica of the object. So for the case of the Fresnel by prism, and assuming that we want to have the highest field of view of the interferential fringes, the separation between the two replicas depends on the size of the lateral size of the Fresnel by prism being half of the lateral size of the Fresnel by prism. So in our case, so let's say that your Fresnel by prism is 20 millimeters. So the separation is gonna be 10 millimeters. So it might be a case where we have a magnification of the image. It's small enough so there is no overlay within the sample, and that's great because you can put one of this replica onto the sensor without distorting the other one. But that's kind of like one particular case. In most of the case, what we have is the overlay, the spatial overlay between the two replicas of the object, and this is what we have right here, right? So you want to increase the magnification, because usually increasing the magnification means to have objective lens with higher numerical aperture if you don't want to change your tube lens. Thinking about adding an external module to your DHM system, you don't change the tube lens. The only thing that you have access to is changing your objective lens. So you increase the magnification because you want to have a higher numerical aperture objective lens, but that might means that you're gonna have two replicas of your object that they might overlay. For the particular case of the Fresnel by prism, you see that this replica right here, kind of like the background is kind of white, so that means that the two replicas, there is a phase shift between the two replicas of the object. So one of the replica has pi and the other one has minus pi, so there is like a phase difference of 2 pi between them. So we don't want to have that overlay. So how we can create a common path digit system without an overlay still being compact, right? Because we still want to have an out system that is compact. So the first way to do it is like, all right, so I'm not gonna do anything. My system is what it is, and I know that there is an overlay, but I'm gonna put my sample occupying only half of the illuminating field of view, so the other half is gonna be the reference wave, and in that way I don't have any overlay. And that's good, it's an easy implementation, but what is happening is that you are restricting your image field of view. So usually if you want to screen a large field of view, that's not suitable at all. The other approach is about, alright, so let's use some kind of polarization-based common path. So let's use here a beam splitter, a polarizing beam splitter, and we're gonna have, using polarization, we're gonna reduce one of the overlays created by the system. So that's how we're gonna create the overlay, and that's super good. The problem is like you are reducing the intensity at the end using polarization, so your system might be more sensitive to noise, and also that technique has been not proven to be used with samples that they are spatially dense. So let's say samples that they occupy a lot of the size of the field of view. The other approach is to somehow filter in one of the object replica. So that means that introducing a relay system and analyze and in the Fourier plane of the microscope inserting a pinhole. So the pinhole is gonna do is it's gonna restrict the frequencies coming from one of the replicas in order to create this kind of uniform reference wave. And you can introduce another lens to put the image in, to create the image in a conjugated plane. So that technique has been used with the Fresnel biprism and also with a tilted beam splitter. So for the tilted beam splitter, that was a dual mode quantitative phase imaging plus a fluorescent microscope. That's a really good technique. One of the main constraints is that the alignment. So the position of the pinhole needs to be a particular position. So let me talk about that approach a little more. So let's assume that right now, instead of having the regular Fresnel biprism in front of the image plane, I introduce a relay system using L1 and L2 lenses. And I don't introduce anything, so in the image plane, the conjugated image plane, I'm gonna have the overlay with the two replicas. And remember, there is a lateral displacement with the two replicas. Alright, so let's assume now that I put a pinhole in the Fourier plane of the two lenses. So that's gonna be the common path, the common plane within the two lenses. The pinhole, the size of the pinhole is such that only low frequencies from one of the replicas are allowed to pass. So this is how I'm gonna create an image without the overlay of the replicated object. So let's talk about how that's gonna work. Alright, so let's assume that you have an object and your object has it's a sum of different cosinusoidal functions with different periods, right? And this is exactly the image that you have in the image plane. And now, if you analyze the Fourier transform, which is the information that you're gonna get in the Fourier plane of the relay system, because it's invariant in the x-axis, so you're gonna have an infinity sum of frequencies along the V, where V is the spatial frequency along the, in this case, is the horizontal coordinate, right? But all these infinity frequencies are gonna get filtered. And let's say that I have a pinhole where I'm selecting only the center frequency, the DC frequency. So when I come back to the conjugated image plane, what I have is a uniform beam. So I have a uniform beam, that's my reference beam. So this is the whole idea. We want to put a pinhole to kind of crop, to clip all the frequencies except the DC terms. So we're gonna create a reference beam from one of the objects, spectrum of the object. So we did that experimentally. So this is like a pinhole of 2 millimeters, which is roughly no pinhole, and then with a pinhole with 30 millimeters. So those are in the first row. We have here the holograms, and we can see like right here is the other side of the images where we don't have any information on the hologram, and this is the corresponding reconstructed phase images. and we get the information of the thickness, and this thickness, the experimental thickness for the 30 micron star target coincides with the theoretical one, and we were kind of changing the exposure time because when you keep reducing the pinhole size, there is a reduction of your intensity. So ideally, your intensity goes to the DC term. The DC is zero frequency, but that's kind of like theoretically, experimentally, that's not true. So you might slightly increase the exposure time of your camera to have fringes with the same contrast. The increase was almost double, from 2 millimeters to 30 microns, but still the exposure time was really low, like to around 800 microseconds, allowing us to have live imaging.
In summary, what we covered in this talk was, first, we learned the basics of the optical recording stage in DHM, that is, we studied the different DHM setups. Later, we studied the difference between telecentric and non-telecentric configuration, but also within image plane system and out-of-focus recordings. We studied those topics in terms of the advantages and disadvantages in each case. We also studied the mechanisms, or better, the systems to provide or to generate phase-shifting holograms in inline DHM configurations. We also recognize the functioning of the reflection DHM system for non-biological samples and without losing sensitivity, without losing spatial resolution. And finally, we appropriate the fundamentals of common pulse self-interference DHM systems. We study the difference when compared to conventional Mach-Zender-based setups. We would like to thank our collaborators all around the world, our collaborators in Colombia, in Spain, in the US, and in Belgium. The funding that we received to make this research, that is the University of Memphis, the National Science Foundation in the US, but also Universidad de Anfid in Colombia, the Minister of Sciences in Colombia too. I would like to also acknowledge the participation of different integrants of our groups, both for Anna's labs and my labs back there in Colombia. And that's it. I hope you enjoyed this talk and see you in the next delivery. Bye-bye.